with that, I'm going to start the presentation. So this title really, there's a lot that is behind this title. I want to explain where I'm coming from with this. And it'll kind of go towards explaining the concept in general, and we'll be going through that same concept over and over. But in general, I'm trying to say that I know they're creating functions, R-type functions for Essbase, where you can include that in your calc script. But what I'm trying to do is approach it from the opposite direction, saying that we can use Essbase as an engine for more machine learning type activities. And that's what we're going to do today, is go in through and use the cubes themselves to generate some clustering that kicks out some results that you then have to interpret and work with, as opposed to using a function that's going to tell you, give you a prediction or whatever these functions might be that are coming out in the new Essbase 12 that I haven't really looked into yet. So it's kind of a catchy title, but the idea is that there's a native functionality in Essbase that's really attuned to some of this machine learning stuff that's going on. And I think that we have a lot of opportunity to take advantage of that we haven't necessarily yet. And I'm hoping that you'll agree after we go through this presentation. So what we're going to be doing. First, we'll just talk a bit about machine learning. I think part of the goal of this presentation is to and it was the goal for me in the first place, to understand what's going on out there in terms that make sense to me. There's a lot of talk about the impact of machine learning and AI, and it's a big deal. And I know what we do is not really directly connected to that, but I think it can be, and I think we can understand it through our lens. And so for me, Essbase is a natural tool and a natural way of thinking even. And going through this exercise through the lens of Essbase helped me really concretely, discretely understand some of these machine learning concepts through the Essbase lens, which is the one that I know. And I'm hoping that we'll be able to do that in this presentation together. So first off, understanding machine learning through the lens of Essbase, and then what does that mean to us? What, as analysts or consultants or developers or just people in FP&A in general, which I think is most of who's using this tool, why is it relevant to us? And then I'll get into basically this experiment of trying to do some specific task, machine learning task in Essbase, and we'll talk about it. And again, I want to talk about it along the way because it's going to get a little bit weird along the way, and I really want you to speak up, but you can't audibly speak up, but you can type in the questions, and I see them here, and I'll read them out to the group, and we can stop along the way, because the goal is just to be on the same page. So first off, what is machine learning? And I'm taking it from a perspective of the impact. What is the impact of machine learning to the world in general? And I just pulled this slide off of the internet, and we see here a ton of impact: prediction, estimation, forecasting, optimization, and recommendation engine is something that I want to latch on to. A company that I worked at for a long time before I became a consultant was really trying to come up with a recommendation engine. They had a bunch of different, basically infinite variations of configuration for their products that was really cost prohibitive, and they were trying to drill down to and focus to and recommend to some specific configurations that would get most of the job done but would bring costs down a lot. And so they were kind of struggling as to how to do that and how to integrate that into their business. And I think that's kind of a thread that we can take through this discussion of all these tools that we see here are great, but how do you integrate them into your business? And I think that's what we do with Essbase and planning is that's literally what we do is we're integrating everyone together. So how can we take all these cool tools here and integrate them together? So yeah, I slid in FP&A in here because it's not mentioned, which I found interesting. Again, to the question of, are we part of this revolution? Are we falling behind? Is it irrelevant? The question that we'll talk about through this presentation. Again, this slide, again, in terms of impact, this is, when you talk about machine learning and AI, and we'll talk about the difference between what all those terms are, but in general, to me, the big deal is the self-driving cars. I mean, when you think about the impact that that's going to have on society in general, I don't think it's even possible to really understand how big an impact it's going to be, but I think we all pretty much agree it's happening now. So I just threw this in here. What does this mean for us that are using this Essbase tool? I know I've gotten a lot of people that have said, well, you have all these cool modern tools out now. Essbase is 90s technology, and it's not really relevant anymore. So are we being left behind by doing this? And then we bring into the picture this idea of Oracle Analytics Cloud, which is Essbase 12 and Essbase in the cloud. It's pretty much the next frontier. They're not really talking so far about on-prem Essbase 12. But what you have with this, I think, it's new to everybody and we're starting to investigate it, but what I think you have is a lot more power. And I'm interested to try to test that power out and leverage that power. So here we are in a situation where we have a more powerful tool being afforded to us and more flexible and easy to use. How can we put that to use and do some more interesting things to be relevant in this environment that's quickly coming upon us? And I think that this presentation is trying to talk to that. But before we get to that, I just want to go back and define, from my perspective, what we mean by machine learning, what we at least care about from machine learning and AI, big data, all those topics, because they're all floating around out there, and you ask 10 people and they'll give you 10 different answers, and I'm going to give you mine. And mine's not trying to encapsulate the entire world of machine learning and AI, and especially in this presentation. What I'm trying to do is just drill down to a specific function that it generally does that we can apply. So first off, neural network is a term you hear related to machine learning and AI, and I'm just going to call that creating groups and putting stuff into them. And when it comes to what's the difference between all this stuff, I really want to just drill down saying artificial intelligence is really machine learning plus a bunch of other stuff, maybe. And machine learning is really clustering with some other stuff, maybe. And then big data is just kind of the lake or the landscape upon which everything sits. I mean, the real reason that all this stuff is becoming relevant now is because we have the data. It's kind of worthless without the big data. But when people talk about big data this, big data that, I think now in general that's no longer really a term that people are using. It used to be the big term, the big buzzword, but now it's not really about the data. Yeah, the data is there underlying, but it's about what you're doing with that data. And so for the purposes of this discussion, I'm just trying to drill down to the concept of clustering as saying that's generally what we're trying to do here. And what is clustering? It's putting stuff in a group. So again, when I'm a Finn, as in from Finland, and I read somewhere that Finns like to just say it as few words as possible, which gets me into trouble a lot. So that is what I'm trying to do here, is not pontificate, but really just focus on putting stuff in a group. That's what we're doing here. So, you know, in this case, what we're seeing here is some machine learning application that's going through pictures and putting those things into a group. And that's what we're going to be doing here in Essbase. So with that said, why do we care? What does that mean to put stuff into a group in Essbase, and how is it relevant to the stuff that we do every day? Well, and this is kind of one of the motivators for me in the first place, in that I'm seeing all this stuff going on, and I guess it's cool and a big deal to be some Google engineer or working from some hot tech startup, but I've always had the feeling that what we do with Essbase is really, we're managing complexity. What you're doing in this FP&A departments, you're managing really complex organization and threading it all together. And I think that's as tough as anything. There's a lot out there in the world. If I just skip back here to, skip back to that slide, there's a lot of these products and applications all coming out, and that's great. You can start something from scratch, but what we do in our business every day with Essbase and planning is we thread all that stuff together. You know, I'm sure everyone on this line probably knows full well about how you deal with 20 people who have an awesome idea that just happens to conflict with all 19 other people, and you have to then figure out how to make it all work in one coherent organization. So I really see that our role, and whether it be in an FP&A department in a company or just more in general, our role is going to become more important in trying to organize and keep together all of these cool new products out here that start to create an ocean of data that conflicts with all the other products. So in general, we are relevant to this whole complexity explosion. That's why I think we need to talk about it in the first place, and also step up and say, hey, we can play in this game too in a second. And that's what we're going to try to do here. So to that end, this is just the story of how I came to this idea in the first place. For some reason, I got onto TensorFlow, just, you know, surfing through the internet. And TensorFlow, you may not have heard about it, is now essentially the engine behind Google search. So when we talk about these hot topics of artificial intelligence, et cetera, I mean, you think of Google. And when you think of Google, really, this is this TensorFlow program that's running the search algorithms. And TensorFlow is an open source framework, essentially, that everyone can use now. But the name TensorFlow refers to tensors, which, and here's where the kind of the spark happened for me. Tensors are multidimensional cubes. So the idea that, you know, the hot AI is really just shuffling around a bunch of multidimensional cubes sparked to me the idea, wait a second, that's what we're doing all day, is shuffling around multidimensional cubes. So maybe we are doing TensorFlow in what we've been doing for the past 10 years in these large organizations. So maybe I need to look a little bit more into what's going on with this. So that brought me to, like I've been saying, doing one of these, okay, what does a TensorFlow mean? What does it mean to manipulate the multidimensional cube to get to what they're doing versus to get to what we are doing? So that brought me to this concept of non-negative matrix factorization, also known as non-negative tensor factorization. It's a cool, confusing term that I brought up, and people around me know that it isn't a term that exists, and have no idea what it is, and they're annoyed every time I say it because it's super nerdy, and we don't need to get, well, yes, we do, and we are going to get into exactly what it means. Sorry, you're on this ride with me, but we will get there over time. You know, where there's a lot of slides left that we'll keep rinsing and repeating. But in the end, essentially what it means is matrix multiplication and the non-negative means it's only positive numbers. And the kind of the impact of that with this crazy picture here is that you break things down. Let's say you have a huge database of faces. You break that down with this process into a subset, basically the parts of a face. You see there in that kind of big NMS picture, that's all the parts. And those parts are multiplied by kind of a weighting to get to essentially your original face in the database. So you have this original database of all these faces, and this tool just kind of creates some canonical parts of the whole, or essentially the same thing that a recommendation engine would do. Instead of having every exact face in there, you have kind of just some general parts that then get threaded together, and it's a lot smaller subset, but it gets you almost back to your original state. And again, we're going to talk through this, but it's just a technique that's the technique that they're using with these matrices and cubes, and we'll talk about how that's relevant. So again, this concept, and here's where we get theoretical, and please, again, type it in there if something just is not making sense. But essentially, the idea of non-negative matrix factorization is that you can have two smaller matrices or cubes that multiplied together equal one bigger one. That's really what it boils down to. And this process, all it's doing, it knows nothing about the data. All it's doing is it's coming up with these two little matrices that I'm going to call them cubes. These two little cubes that multiply together equal this big cube. And again, we're going to keep talking about what that means. We'll go through it. So here's an example of one big cube or matrix. And this is pulled out of Wikipedia. So across the top are articles, and down in the rows are words. So like you see here, antibiotic resistance. The second article has words like behavior, contact, disease, gland, infection. And the first topic, gardens, has words like flowers, growing, leaves. Anyway, that's just okay, I got a question here. So basically, it's vectorized operations. Yeah. Yes. And there's as one part of it, which I think is what we do. Sorry, let me restate that. I forget. People don't read it. So the question is, so basically, it's vectorized operations. And I think, yes, essentially. And we'll talk about what that means. So here's our original database. And so what this matrix factorization is doing is trying to distill that database down into two smaller ones, distill that cube down into two smaller cubes. And we're going to talk about what exactly that means. So, for example, let's say you have your original database, 2,500 columns, 5,000 rows, that's 12.5 million cells. And this process can break that down into two smaller matrices that are 10,000 and 20,000 cells respectively. So that's baking 12.5 million cells into 30,000. So that process, you're densifying cubes. Instead of having one huge sparse cube, you're making that into two dense ones that multiply together equal that original one. So that's a concept that has no idea what your data is, no idea how you're trying to organize it. It's just doing a very simple, I don't know if simple is the word, but very straightforward, mindless procedure of baking that into two denser cubes. And again, now we're starting to talk in Essbase terms. Everyone knows about the value of making things dense, and the value of knowing sparse versus dense. So here we go, and we're starting to do some natural activities of Essbase with this non-negative matrix factorization process, which I'll call NMF. So let's take a look at what this actually looks like. So now you have this little cube on the left and a little cube on top that multiplied together equal this bigger cube. And I'm going to now give some basically, I'm going to call these columns and rows, I'm going to give them a name, because that's essentially what this is doing. And this is kind of the key to the whole thing, is that by doing this process, this NMF process, you're creating groups. You're creating general groups that then come back together to make up the original. So like, let's say here, State of the Union, that third column, it's actually going to be part coordinates and part governmentness. That's going to, so you look at your coordinates column, and again, this is kind of the idea, is like we now have to give names to these groups that this mindless process creates. But if you look at the coordinates group, you have words like constitutional, council, culture, government, justice, the governmentiness, Congress, elected, governor. So if you now look at this State of the Union column, the third column in the big matrix, and you look up above, you see that it's taking a little bit of coordinates and a lot of governmentness. Basically, that cube above is the factors. So it's taking, essentially applying a factor to the coordinates group and more of a factor to the governmentiness group. So now you're defining this entire original database in terms of groups. And you're mixing, each column now is a kind of a mix of the different groups. So instead of having to know, 2,500 articles, you just can have 10 groups, and each article is somehow a combination of these groups. And that's not perfect by any means. You're not going to get exactly back to the original amount of words in each article, and that's a little bit of a departure from what we're all used to. There's no such thing in our world as, well, it's close. That just doesn't exist. We're tying out in the end, and this is a little bit different than that. But again, we're going to keep going through this and put it all together. But the general idea is that now you've created groups. You've created groups. So we can also apply that to different activities in your business. Let's say we applied this to fixed overhead. So across now our cost centers and going down our accounts. And you go through this process, and you can say like sales support, column 4. That's really just a mix of back office stuff and project stuff. And you see in the projects column there, what's in projects, wages, some temp. But what's really illustrative of this process is, like, look at I don't know if you can see my arrow, but the back office versus plants columns. So plants have non-exempt wages and overtime, whereas back office have exempt wages and bonus. So this naturally, essentially, is creating an account hierarchy that, we intuitively know that from our business, that exempt wages are for the white collar and non-exempt are for the plants, but this is finding out those trends on its own and creating those groups, essentially plant costs and back office costs. Okay, we got another question, which is not clear in forming the big matrix. Any hints, please? Okay, I got you, and we'll go through that, and it'll take a bit of time, but let me just address the idea of matrix multiplication. That's basically the key concept, which is to get to this number here, and let me back up to the actual numbers up here. So to get to this actual number right here, this 10, you're going to be multiplying this number. And Karen, can you tell me if they can see my where my cursor is?
Yes.
Okay, I can. So, and I have a a picture of this later on, but let's try to just address right here. This number 10, in terms of multiplying two matrices together, multiply this number times this number plus this number times this number plus this number times this number plus this number times this number. And that's it. So that's, if we were to multiply these two matrices or cubes together to get to this big one, that's how you get to those numbers. So this 10 is, 0 times 0 plus 10 times 1 plus 5 times 0 plus 0 times 1 equals 10. So does that start to clarify a bit how we get to that number? And if not, we'll keep going and we're going to talk more about that. But that's the general idea of this process, is that by multiplying these two together, you get close to the original. And maybe the original number, let's see if I have it up here. Let's go back here. So the original number here is actually 9. That's the actual original matrix multiply. All right, here's another question. Is it matrix multiply as in math? Yeah, exactly. So if you type in to Google matrix multiplication, it'll talk about this concept, how to multiply two matrices together to get a third. And that's kind of the whole point of this thing, is that, and again, it's kind of a big topic, and we're going to keep going through it, and I'm trying to just take it bites off at a time, and kind of bear with me as we get through it. But essentially, that's it. All we're doing is math. We're multiplying matrices. We're not doing any weird calculus. We're not doing anything but just multiplying matrices together, aka doing cube operations, the stuff that's native to Essbase. By doing this straightforward math, even though it's scary with matrices, it is, in Essbase terms, kind of logical, because it's something that we do all the time. By doing this kind of just math, mindless math, in terms of you don't know, you're not giving it any parameters or anything, you're just multiplying matrices together, naturally you come up with these categorizations that then can create natural clustering. So in the end, let me keep going with where I'm trying to go. So let's say you add a dimension to this. So far we've just talked about two dimensions, like cost centers across the top and accounts going down. But this can go into as many dimensions as you want. Now is where we start getting into Essbase thinking, where I feel like this is where we have a leg up on a lot of people out there, where we think in these terms already. And granted, I haven't tried, I've done this just in 2 dimensions so far. So trying to add a third, I'm not exactly sure the implications, but I think that's kind of the interesting challenge and the fun in this, is that what does exactly it mean, and you have the freedom to organize it the way that it makes sense to you, as opposed to just typing in a function that gives you a result. But theoretically, in this case, we throw in the time dimension as well. We can start really seeing clusters of activity that happen. Plan projects will spend a lot of money at right before the plan is created, in the middle of the year, and then the facilities will spend a lot of money at the end of the year, and the back office doesn't have a specific time, and something happened in the plants at this specific time that was really when there was this big adjustment done to benefits. So essentially, what you're doing with this mindless math, matrix math, is you're creating these clusters and these groupings that explain your business in terms of topics. That's really it, is you're creating these topics, which is when I was in an FP&A department as an analyst for a while, and that's all we did all the time was, we tried to explain what was going on in terms of a story, in terms of topics. And this is a process that naturally will create topics for you. It's not going to name the topics for you. It's just going to find things that happen like each other, like general trends that happen. And you as an analyst can then run with that and say, oh, everything seemed to happen in plant expenses at this time of the year. Oh, it was because of this benefit change that we made. But this is, I think, the next level of analysis that can really help not only an FP&A department to break down and find the trends that are going on in your existing data, but also, and when we talk about ASO world, I know we're doing a lot of applications that are not purely finance, but are more product related. You can imagine taking a product cube that has, however many thousand members in different dimensions, doing this type of analysis to see, oh, it looks like generally we can describe most of our business through these 5 or 6 product configurations. I mean, that's really gold in terms of what businesses are trying to do, especially when you implement that in your existing tool set that has the data already in it. And not to mention, for us who actually do this for a living, this could be a big deal in terms of a new industry, even a new horizons for what we do with this newer version of our technology, Essbase 12 in the cloud. I'd love to really put it through its paces and start doing some more of these really analytical, clustering, machine learning type topics. So that's the cell. That's the idea in general, that we could really make use of this concept. So with that, now I will talk more about what that actually means and how you actually would do it and implement it in real life. And before I do that, any reactions to this? I know it's pretty theoretical, but it's just a beginning to get you interested in the concept. And as we talk about how you actually do it in Essbase, it's really a first step. Just checking the time. This is actually going to be a presentation that I'm not totally short on. I'm going to have to try to speed it up and not go over. I want to leave some time in the end to talk about it too, at least to get your questions out. This is just trying to conceptualize how this works. The concept of least squares, a lot of people know just from statistics or in the past, that you can create a function that will generally describe the best balance of all of these kind of disparate activities that go on, and that's great for a linear problem. But this is exactly what we're trying to do, but it's non-linear. And this process is a process to get to that. And generally these non-linear processes, like goal seek in Excel, you do it iteratively. There's not a function that just gets you to the right answer because there's not fixed points. So that's what this process is doing, is it's basically instead of finding a line one line amongst all these dots, it's finding these 2 smaller matrices or cubes that then together would multiply to create this original disparate data set. And so we'll talk about what exactly that's doing. And this is the kind of the common terminology that you have, like a W and H matrices multiplied together equal this WH. So what I'm going to do is I'm going to go through all this terminology, because this was the thing for me where I saw this concept. I knew they were talking about cubes, and just what exactly was this terminology? It took me a long time to figure out exactly what it all meant. I want to get that across, because in the end you're explicitly defining exactly what to do to make this kind of magic clustering happen. And this idea is this V was the original matrix, all your articles across the columns and all your words down the rows. And then these 2 matrices, W and H, multiplied together equal this WH matrix, which is kind of almost the same as V, and your goal is to get it as close as possible. And you'll never get it exactly the same, but you'll get basically your best fit. Just like here, you're not going to get to all those points, but you're going to get to the best fit for all of them. And it's a different concept, but this kind of illustrates it in a way that we're getting to just our best fit that we can. And to that end, there may be situations where there's not a great fit, there's not a great correlation, in which case it doesn't help. But if there are cases where you really can represent some sparse matrix in terms of something more dense that creates these topics that are very succinct, then you really can create some value through this process. I'm just going to kind of barrel through what this actually means. So to get to that, to someone's earlier question, these are the three elements that we need here. So it's doing my GIF here in the slide, which I didn't realize it did. But matrix multiplication, this one on the left here, this is what I was talking about before, where you multiply A1 times B1 plus A12 times B22 to get to this result here. So this is that process, and we're going to talk about how we do that in Essbase. The second one is transposing, which, let me start it over here. That's where you take one, you basically just flip it, and it's going to do it here in this GIF. I didn't realize I'd do it, but you see how it just flipped it there? That's all it is. And then the third is just the basically regular old cube math that we do in Essbase already. So what I'm saying is that we can create clustering, we can create recommendation engines, we can create topics for analysis to research further, all through these three simple operations, which are very Essbase, in that there's not calculus. You're just doing, you're really literally multiplying, dividing, subtracting, and then rearranging cubes, or rearranging matrices. So I have a comment here. These ideas sound similar to Andrew Ng's machine learning class on Coursera, which uses Octave. There's a lot of matrix multiplication. Is it possible to do all of that Octave can do in Essbase? Can you walk through a calc script and outline that does some of this? Yes, indeed, is my answer. Yes, it is possible, which is what I think is so cool, and yes, I will walk through that. So that's my whole idea, and I did not know it was possible, and it was, but yes, I actually proved it out, and we'll go through it. So I'm going to break down now exactly what this terminology at the bottom means. This is the algorithm. You know, we talk about algorithms as part of machine learning. Well, here it is. And also for solving nonlinear problems, algorithms, here it is, a recursive algorithm. And I'm going to explain what that means. So let's go through it here. So let's look down below. What you have down below are two recursive algorithms. One that basically gets the W matrix better fitting, and then one that gets the H matrix better fitting. We're just going to focus on the H one right now. So what that does, let me back up here. Oh, sorry. Start over. Okay, so you have this, I look at just this one here, and again, what this is saying at the top, Euclidean distance V minus WH is non-increasing under these update rules. What that means is we're trying to get V versus WH to be basically the same. And the smaller the distances between them, the better off you are. So if you could totally recreate this huge sparse cube with just these two little ones, then you basically organized your entire company into a lot smaller. Basically, you found the topics instead of looking at all these pieces of data, which is the goal, kind of the goal in general. You're never going to get one for one, but you're going to get close, and that's what this is talking about, V minus WH. That's getting these two as close to each other as you can, and we're going to talk more about what exactly that means. So to do that, step one, let's start with this WH and this notation. That WH equals this WH matrix. Let's look at WT. That's W transposed. So all you're doing there is you're basically, in terms of Essbase, you're rearranging the numbers in a different way. So like flipping essentially the order. So what was number 1 will now, if you have 10 members, member 1 will now be member 10. And that's it. That's transposition. So now what this is showing, what did I do here? So now, sorry guys, I'm going through going the wrong way here. Bear with me 1 second. Starting over one more time. Okay, so WH is that. WT is that transposed W. Now both of them together, you're multiplying that transposed WT times your WH to get to this WT-WH. So that's just, you're multiplying these two matrices together, same as what you did originally with WH. Again, the same process that gets to this third now matrix. And again, up top, this WTV is doing the same thing where you're multiplying this W transpose times the original V matrix to get to this WTV. Then, and this one had gotten me confused when I was first trying to figure out what's going on, because it's like you're multiplying what times what now? Because now you go and you divide those two by each other here. I'm trying to get my panel out of the way so I can see it here. So now you're dividing that WTV by the WT-WH. So that's these two matrices here. But in this case, it's element-wise, which means you're literally dividing every cell in this by every cell in that. And I can speak to you in those, in Essbase terms there. We're essentially just dividing scenario 1 by scenario 2. It's like a straight ahead division. And let's say you had, your entire cube of scenario 1 divided by your entire cube of scenario 2. So, regardless of how many dimensions it is, the math still works. So those two divide, the one divided by the other equals this WTV divided by WT-WH. That's this whole thing here, is this final matrix. And then the last step is you multiply that whole thing by the original H to get to a new H. That's what this little arrow means. It's like now you have a new H that you then replace into your original. And that's the iterative, the recursive algorithm right there. That's the process. So, it's some crazy math here that's, very scary and complicated, but in the end, all you're doing is simply multiplying these different matrices or cubes or slices of a cube together through this process, and the result that you get, you're plugging back into the original. And as you keep doing this process, H will always get better, and at some point it's going to just get as good as it's going to get and not get better. But the idea is that you can whittle it down. So you do it with the H, then you do the same thing on this side with the W. Go back to the H and just kind of whittle it down until you've gotten to the best W and H that make WH be as close as possible to V. So this is just a purely mathematical process that has no idea about what it's doing, but naturally through this kind of densification of the original matrix, you've created these groupings, you've created this clustering, which then you can apply to all these topics that businesses, I know from my experience, are looking for. And you do it in your existing tool set and, apply it to the existing jobs of your analysts. So here, we're already running out of time. I'm going to keep going through this here. So again, this is that idea of matrix multiplication that we just looked at. But now, to the earlier person's question, doing it in terms of Essbase, where we now look at this in terms of a cube. So I've taken this cube is the same as this matrix multiplication. So again, these could be, this is your H, and here's your W, and here's your WH right here. And again, now this is the same thing in a cube form here, where you're putting your W here, and I'm creating 3 dimensions here, dimension 1, dimension 2, and dimension 3. So you put your W into this spot in the dimension 1, 1 through 4, dimension 2 at 0, and then dimension 3, 1 and 2. And I know I'm just saying a lot of numbers now. Here's your H above. So instead of, I'll go back to the original here where it has it spread out, you're collapsing those into a common dimension here. So now you can do naturally some Essbase operations to get to that result. So here, for example, this one cell would be essentially, W times H in that cell, and you can just create a script that does it for everything at once. So you're fixing on the relative 0 of these 3 dimensions, and this calc here will multiply basically the 0 above times all these guys, basically the intersection, create the intersection of these 2 cubes, and that gets to your result. So in the end, when you sum up this dimension 3, that sum, that roll up is going to be the same as going back to here and getting to this times this plus this times this. You sum up to is the same as rolling up dimension 3. So that's how you do matrix multiplication in Essbase. So with that, you really just need to know how to do that, and then know how to take a result and flip it around somewhere else, back to that transposition where if it's in member 1, you flip it to the last member. In this case, if it were like it's in D1, you'd flip it to D4. Those 2 operations are all you really need to know, that and just general Essbase knowledge. With that, you can go back and do all of these steps here and run through the entire process and iterate it back and feed back to your original H intersections and get to that final result, which I've tested out and done. And see what else I have. So basically, yeah, that's what I'm saying here is that we have that, we have the transposition, and then this is, the element-wise division, multiplication. That's just classic Essbase calc scripting that that we have in our pocket as well. So this is saying you have all these tools. If you just put them together, you can get to that final result, which is that basically doing not basically, but literally doing machine learning tasks natively in Essbase. And instead of using a function that tells you what to predict, you're actually using the tool itself to generate naturally these clusters that then you, as an analyst, take and give names to. You can, just thinking about it, you could create automatic hierarchies for members based on how they roll up, like plan expenses versus back office expenses or what have you. I mean, the possibilities are kind of endless. You could do recommendation engines. You could do analysis topics that you see, wow, something really happened in this intersection of months and cost centers and entities. Let's go see what it is. And you realize, it was because we had this one sales initiative. That's a great tool to go do that analysis. So, and in general, the idea is that, we've talked about the most intense cutting edge global disruption topics in the world right now. You know, Google, TensorFlow, and machine learning. But when you look at it, it's really close to what we do all day, every day anyway. So that's the first thing I wanted to get across, is that, you know, we're doing this stuff and we should be a part of this explosion of this golden age, they're calling it, of machine learning. And I think this is a method to do that. And with the tools that we have coming down the pike now, you know, the cloud-based tools that theoretically are a lot more powerful, we can leverage this to do more things that I think can spread the industry for us. And that's really what I was trying to get across. And we have a few minutes left here, and yeah, kick out any questions. I'd love to hear anyone's impressions or questions. A little bit tougher without being able to talk, but that's my idea. And I can pull up more specifics. Like I have a cube that I built doing this, but we just we're out of time pretty much.
John, we can wait a few minutes for any questions that might be coming in.
Well, guess while we're doing that, I can take a look at this cube. You pull up the cube where you've done this and show us more detail. So I'll do that here. Let's see if I can share it here. You guys, do you see my screen here?
Yes.
I can also bring up some Excel that shows the process too. Like here's my initial run through in Excel. I can share out to you guys, but essentially this is doing the same process where I add that list of all those matrices multiplied together. Well, here it is in Excel. Here's a V, here's, you know, W transpose, and that's the result. And then here's WH and WT and the result, and then you just basically multiply those two together and then divide, et cetera, et cetera. I'm skipping too fast through it, but yeah, this is ridiculous to try to explain at the moment, but essentially, you know, if taking enough time, you can go through and match each of these steps here. Like I'll just match one here. So here's W, here's H, and here's WH, which matches back to you know, this WH and WH. And let's look at it in Essbase too. So in Essbase, the idea is here in this outline, I have this NMF here. So the trick is to log in like 90 times until the time is run out, and then you just shut down. Okay, it worked. All right, it's nice. Always interesting to make jokes in a totally silent room. But so okay, let's see here. How do you generate the calc script when you have dynamic dim? So have you used this in a real life situation? I've not done it in a real life situation. Let's answer the question of dynamic dimension. So here's my, you know, dimension 1 here. Here we have another 7,000 members, and I've thrown in these levels just to help calculation. Because, you know, like a dimension, a sparse dimension with 7,000 children of a parent is an interesting experiment in terms of calculation. If I drill into one of these guys here, in fact, yeah. So here's the number, and the alias is the actual word, relegation. And if I go and check out a different, change the alias to the reverses, I've created a reverse for all these members. So essentially, the last member here of 6925, its alias is 1 with an R at the end. So essentially, in terms of dealing with dynamic dimensions, you need to know always essentially how big your dimension is when you load it, and have a way to put your alias so that it's flipped. And then when you do that, you can either reload your data with an R to flip it, or use a calc script to flip it. I did this to reload because of block creation issues. When you're dealing with all this kind of data, you get into those issues pretty quick. But an earlier version just used a straight, shift calculation to just flip the values in a dimension. But essentially, so you have dimension 1, that is essentially this, the W going the rows, aka the words. Dimension 2 are the columns, aka the articles. So if we look here, it has the same concept going on. And let's look at a calc. Let's look at first example of a calc, like to calculate H, like the first step of that. So hold on a second. Let's not look at H1. Let's look at H11 because that's different. See in my calculator, I'm doing a lot of exports to reload in that kind of flip it and create blocks. But essentially here, in terms of your question of how you do it with a dynamic dim, notice here I'm looking at D3, D2, and D1. You don't need to know anything about how many members are in the dimension for these calcs. I could put in 1,000, I could put in 10,000, I could put in 5, I could change it up. That's kind of the cool thing about this, is it's totally dynamic. You don't need to know. All you need to know is when you load a dimension, you need to have in your load file a reverse alias, essentially. Like, you need to know when you load it in that you have 1,000 members, and that the first member is going to have an alias of 1,000 reverse. That's the method that I did to load it in and to create blocks. But in ASO, theoretically, you can do just straight up calculations and not even have to know about that. But in terms of the actual calc that I referenced before of really doing matrix multiplication, you don't need to know anything about the dimensions themselves. I'm trying to now look here at the panel here and see if there's more questions. No, that's it.
I haven't gotten any more.
And I'll just show you. Okay, and I guess we're out of time. I'll show you one last thing here real quick, which is just a check here that's showing this has your whole situation. All those cubes we looked at all laid out here. Here you have your V and your H and your W and your HW, and then here is your V minus HW. And as this number goes down, every time you run an iteration, it goes farther and farther down. You know that it's working because it's the delta between HW and V. So that's an overall, just looking at this process in general. And I guess we're at 12 o'clock. So I hope that this was interesting, stimulating, and that it gives you a feeling that you're in the race with the coolest technology out there and what you're doing. And with that, I guess just say thanks. And I'm John Keski on Twitter if you want to ping me for whatever reason. And yeah, thank you.
Thank you, John, for being with us today.